Thank you for the invitation. I'd like to talk to you today about a new type of robot, a new class of robot that we're going to need in the near future here when we go to the moon and Mars. And we've coined a new term here in our lab called we call them blue collar robots. And blue collar robots work with regolith. So they work with dirt. And these are a different kind of robot. And I'll explain to you why they're different. But first of all, who are we? SwampWorks is an innovation environment. It is part of NASA. It's at NASA Kennedy Space Center, but think of it as a small startup within the government. And we basically are an innovation lab, and we work on in situ resource utilization. We work on robotics to enable in situ resource utilization, also called ISRU. And we try to embrace new technologies. And the basic design philosophy is to fail fast forward, iterate rapidly, and learn from your mistakes, but don't be afraid of your mistakes. So this is different than the traditional aerospace method of working, and we're more risk tolerant, and we're okay with failure as long as you fail in the lab. We're not going to fail in flight, but if you fail more often in the lab, then you will be more successful in flight. That's the philosophy. This is a picture of our lab high bay. It's called the Granular Mechanics and Regolith Operations Lab. You can see there's a regolith test bed. It has 120 tons of regolith simulant, Black Point 1 basalt regolith simulant. We have a smaller test bed, has 2 tons of lunar hylith simulant. We have a vacuum chamber. We have a robotic arm for 3D printing with regolith. We have dirty TVAC, thermal vacuum chamber dynamometers. So it's a robust capability, but the main thing I want to point out is that nothing is permanent. Everything is on wheels. We can roll around and reconfigure very quickly to embrace new technologies and new projects. So I'd like to also point out this autonomy. Oops. This should be a video that plays. Okay. This autonomy test bed. Do you see the video?
Yes, we see the video. Yeah.
Okay. You see the video? This is our autonomy test bed. The previous talk mentioned the IPEX mission, ISRU pilot excavator. That is being developed out of the SwampWorks. It was invented in the SwampWorks and patented here. And so we are building a very small excavator, only weighs about 35 kilograms. And this, with that kind of mass, the weight is very low on the moon, about 7 kilograms. And so you don't have enough reaction force to do anything really. So we had to reinvent excavation. We designed these bucket drums, and they're counter-rotating bucket drums, and they do react against each other. So now you have zero horizontal force, reaction force excavation. And in this test bed, we develop the algorithms. And just as was mentioned in the previous talk, this is going to take a lot of autonomy. So we're developing autonomy as well. So let's get into it. What does blue collar mean? This is kind of a U.S. term. In other countries, maybe they wouldn't understand it if we said blue collar and white collar. So I'm going to explain it just in terms of multicultural aspects. So blue collar in the United States means construction, manufacturing, agriculture, mining, maintenance, etc. It's usually lower education people, manual labor, pay by the hour job. And historically, they wore these blue collar shirts. That's where the term comes from, is blue collar. And then white collar was more engineering, science, management, finance, executive, more highly educated and salary-based pay. And they used to wear white collar shirts and ties or suits in the office. So that was where the term blue collar, white collar came from. And sometimes there's a perception that blue collar workers are lower paid and lower class. And sometimes it's used derogatory term, but when you're in the blue collar crowd, they're very proud of their background, and they wear that label blue collar very proudly, and to them it means strong work ethic, honesty, sacrifice, and community. These are all really positive things, and our country wouldn't function without blue collar workers. It's just a fact. So to celebrate these ideals of hard work ethic, honesty, sacrifice, we call these robots blue-collar robots. It's a new breed of space robots designed to perform rugged, labor-intensive tasks such as mining and construction in a production environment. So this is a different kind of robot. And what does that mean? Well, the production mindset, it's not like most NASA or JPL robots that have been built in the past. In the past, we built very exquisite robots that are scientific instruments. They're very good at what they do, but they cost billions of dollars. And they go to Mars and other planetary surface. They do their job very well, but it's just a very expensive thing to do and very complicated. A blue collar robot, in contrast, is very simple. It does one or two things very well in a production environment, and the highest priority is efficient and reliable delivery of products or services. For example, delivering Regolith. So we've developed this IPEX robot, and all it does is mine robot and mine Regolith and deliver Regolith. That's all it does. And sometimes people come to us and say, hey, we'd like to put a neutron spectrometer on there. Can we put another instrument on there? And no, we don't allow that. It does one thing very well, and we keep it simple. And for example, we have really tight key performance parameters. For example, deliver 1,000 kilograms of Regolith 1 kilometer from a mine site to a processing plant per day. If you are in a production environment and your production line goes down, the cost is very high because your production stops and every minute counts. So these robots have to be super reliable, and there have to be the right infrastructure. So for example, communications, the latencies, the terrain changes, autonomy, all this has to be understood in advance to achieve this reliability. In the science world, the highest priority is to maximize scientific return. So it's a different success criteria. If you look at the table on the right, what is really significant is how little we've traveled on the moon up until now. And you can see that the world record holder right now is the lunar roving vehicle in Apollo 15. It did an average daily travel of 2.76 kilometers in 24 hours, but our IPEX mission will do 5.28 kilometers in 24 hours, 58.1 kilometers in 11 days, and it will mine 10,000 kilograms of regolith. So this is a whole order of magnitude bigger than what we've done before. And then we start to look at the studies and say, well, what do we actually need to excavate? And in the studies, it indicates that even though we think ISRU needs a lot of regolith, it pales in comparison to the amount of regolith you need for construction. For construction, you need, initially estimates were like 589 metric tons of excavated regolith for a 50-meter diameter pad. But then when we looked at it a little bit more closely using the topography models and the cut fill software to see how much you actually had to excavate and deposit, it's more like 40,000 metric tons. So these numbers start to add up quickly. And if you took the IPEX mission that I just showed you, which is a tiny little robot, it only weighs 35 kilograms, and is scaled for delivery by a 100-kilogram payload CLPS lander. If you use that robot, it would take 43,779 days to do that. So obviously we have to do something differently. So here is a CAD model rotating of the IPEX robot, and we need resiliency through layered failure tolerance. So we expect the worst case failure scenarios. We design not just fail safe, but fail operational. So we build failure into the operation. We can tolerate failure. If it fails, we just recover. Hazard tolerance other than hazard avoidance. So I like to say you can hit it with a hammer. You know, it needs to be tough. Select extreme load cases and include judicious margin. So you really need margin on these construction machines because they're going to take punishment far beyond what you think it will. And there will be edge cases where the margin will save you. It can also self-rescue. It can self-right. This robot can traverse slopes up to 30 degrees by shifting its center of gravity. We've done up to 35 degrees in the lab here. which is much more than a regular robot can do. It has redundant mobility. It can drive on the bucket drums or on the wheels, and has redundant excavation implements. We use layered autonomy algorithms. We use visual odometry, wheel odometry, sun tracker, lander fiducials, and IMU, but we do try to keep the amount of sensors to a minimum. Here's just a little video demonstrating the capabilities of a previous prototype. This one weighed about 66 kilograms, and we call this Razor 2.0. It was just part of our iterations in the lab. And you can see how it excavates, but you can also see how versatile it is. It can deliver to the oxygen extraction plant. It can deliver, it can climb hills like it's showing with its shifting its center of gravity on the bottom right. And the scenario in the bottom left of it climbing rocks and then doing a victory salute, that is just to show it's possible. We don't anticipate this kind of scenario, but we just wanted to show how versatile this design is. And that's part of being a blue collar robot, is you have to be able to handle all these contingencies, and that gives you a different mindset when you're designing it. I've already mentioned this. We have to reject scope creep. Scope creep is the enemy of blue collar robots. People always try to add more payloads, creep the scope, but that's against the principle of blue collar robots. Another really big principle of design for these robots is you don't have to do everything. You don't want to do everything, because you can offload, for example, direct to earth communications. You can offload that to the lander. A lot of people thought this wasn't possible because the thermal radiators would just dust up and then the robot would die, overheat and die. So what we did is we offloaded the thermal radiator function to the lander, and we use a phase change material, and we store the heat. And then when we go to recharge the batteries, we also do a thermal reset. So again, you have to be innovative. You have to think differently and just start looking at it as a system, and then offload your functions to the lander or other systems as much as you can. That's how you keep a robot simple. This on the top right, you'll see this a new technology that we've developed at Kennedy Space Center called electrodynamic dust shield. In a minute, you'll see it just clearing, and that's with no moving parts, just electrodynamic forces. And so we have these dust mitigation technologies. We've also developed these actuators. Rotary motion is preferred to linear motion to keep the dust out. We have redundant seals. We have labyrinth seals. We have felt seals. We have 3 different types of seals to keep the dust out. We do extensive testing, and that's how you solve the dust problem. Here's a video of some reduced gravity testing we did. This is a cutaway of the inside of the bucket drum. So the bucket drum is not hollow. It has these baffles in it, these spiral baffles. The spiral baffles is what keeps the regolith in there. So if you rotate it one way, it excavates. If you rotate it the other way, it dumps. But here we did this on a Blue Origin reduced gravity suborbital flight, and you can see that the cohesion on the left is much higher than the cohesion on the right, and it tumbles differently. So there are differences in the way that the regolith behaves in the different gravity. The point is, though, it was successful, and it did work in lunar G. So this design passed this test. The one thing you might ask is, why do we need robots at all? Why do we need blue collar robots? Why do we care about regolith? Well, the moon's resources have been valued at hundreds of billions to multi-quadrillions of dollars. It's a source of resources, and energy is very plentiful from the sun and easy to get on the moon with solar arrays, as was already mentioned in the previous talk. And then that's just the moon. We have billions of other bodies in space. Some asteroids have been valued as much as $10 quintillion. So the first nation that harnesses this resource in outer space will have an inherent advantage over any other nation in the world, and it will produce prosperity and abundance, and it will be hard to catch up with the exponential growth curve that is created by in situ resource utilization. In order to do that, we need the robots. It won't be humans doing this work. It will be robots doing this work. And it's not going to be the robots we have today. It's going to be blue collar robots, and they have to be dust tolerant and regolith tolerant. So that is the message. Thank you very much.
Awesome talk. Thank you so much. So we have time for one quick question. Very quick, yeah.
So I appreciate the, I guess, robots, but so I'm working on the blue collar robots for nuclear waste cleanup. And so in these applications, you can't have humans access the robots, and if something goes wrong, they're gonna have to recover themselves. And I keep thinking humanoid robots are advancing a lot, and they have a role, at least operationally, to help keep things running. What are your thoughts on that?
I'm sorry, I can barely hear your question. So Maggie, could you just give it to me in one sentence?
Sorry.
Do humanoid robots have a role as blue collar robots in space?
Do humanoid robots have a role in space?
Okay, so I attended the DARPA challenge for humanoid robots, and I've also spoken with Gitai about this, who won the DARPA challenge for humanoid robots. And what I saw at the DARPA challenge was that humanoid robots are very clumsy, and you have to make a decision. Do you want a robot that does everything like a humanoid robot, or do you want a robot that does one thing very well? So my vote would be to have a family of robots with distributed capabilities. Each robot has a different function. In the future, maybe a humanoid robot could do that, but today humanoid robots are not robust enough, way too complicated, take way too much power, and is complete overkill for what we need. So no, I don't think humanoid robot is the answer today. Maybe in the future it will be, but today is certainly not the answer.
Okay, cool. Thanks. Let's thank Rob again.